Hi everybody, this is Nafish. Today we're going to go over FM modulation, frequency modulation. So basically there is a very good lecture on this. If you go to the link I provided, this is provided by Stanford University, and this is like kind of you will get very good idea on FM, and I will try to implement the equation right here, okay, which is the output of the FM modulated wave, and also I will try to plot one of these plots right here, okay. So when you guys get time, just go over this document. That will help. But let's get started in Python. So basically, I have imported NumPy as NP and Matplotlib as PLT. Okay. So NumPy, you guys know, like we need for numerical calculations and Matplotlib for plotting purpose. Okay. And then let's define our message signals. So message sig, this is the variable, and then let's define it AM times sine, then 2 times pi times fm times t. Okay, so this is a sinusoidal wave with a single tone. Fm is the message frequency. Okay, and we can just copy this part and try to uh, assign it to the carrier. So let's just change the name here. So carrier. Okay, and the amplitude will be different. Let's say AC, and the frequency of the carrier, you guys know, like it's kind of much higher than the message frequency, right? So this is what we have for the message and the carrier. Now let's define all these terms here. AM and AC, let's say AM is equals to 1. For simplicity, AC is also 1. Okay. FM, let's say it's 20. You guys can put other numbers if you want. And FC, let's say, which is much higher than the FM, let's say 200. Okay. And the sampling frequency, you know that it's has to be at least 2 times greater than FC, right? The carrier frequency. So let's say this is 1000. Okay, that's the sampling frequency, samples per second. Okay, and then you gotta have a delta T, which is inversely proportional to the sampling frequency. This is the sampling interval. Okay, we need this right here. So we have to, you see the T here. So this is the time duration, right? We have to define it here. So T is NP, calling the NumPy library, np.a range. So what this is going to do, we need to have a signal starting at 0, ending at 1, and we need to provide the sampling interval, which we have defined right here. Okay, so delta T. Okay, so this is kind of dependent on the sampling frequency, as you can see. Okay, so we have all of it, I think. So let's run it, and hopefully there is no error. Okay, this part, and then this guy, and here I think I missed one part, which is np.sine. We have to write np in front of sine because this is this sine function, we're getting it from the numpy library, right? Here as well, np.sine, and then pi, same thing, np.pi, and np.pi. Okay, I think we are all set with the message signal and the carrier signal. Now let's define the fm output. Okay, I'm just putting one space here. So fm out. So we have to, so there is a in phase component and the quadrature phase component. Okay, let's write down the in phase part first. Okay, so we got to have the carrier, right? So AC times NP dot cos, and we got to have the same thing right here. We have written here. So just copying that part and putting down right here. Okay, and we are going to multiply this with the message signal. Okay, so cos and then the message signal. Okay, now this message signal, this is, we are going to change the frequency, right? That's why we call the frequency modulation, right? And there is important part to play here, which is the modulation index m is equals to 1. So this modulation index is the ratio of this message signal and the frequency deviation. Okay, and also it depends on the sensitivity of the modulator. Okay, but for now, just taking 1 as the value, and but we'll change it. We will see how that is impacting. Okay, so putting the value right here, m times the message signal. Okay, so we got the in phase part. Then we have to write down the quadrature um, part as well, which is the same thing, but it's going to be a sine rather than a cos here. Okay, so write down sine, and then write down sine. I think I missed an np here, so write down sine here, and then np dot sine, and here I missed np, so np dot cos. Okay, So hopefully there is no error. Let's run it. There is an error because I didn't run this cell. I defined the modulation index later, so I have to compile all those. And now there is no issue. So let's plot all these three signals. Okay. First, plot the mass signal. So PLT dot subplot, because we're going to see everything together. So that's why calling the subplot. So going to have three rows because we have three items, right? And then one column, and this is the first item, which is going to be the mass signal. So PLT dot plot, then T, and then press tab, you got the message signal, right? So I'm just going to copy these two lines and paste two times. So in the second part, second component, going to have this carrier signal, right? So let's call the carrier, and the third one is going to be the FM output. So FM out, and let's change this position to 3. Okay, so I think we are all good. Let's run this part. Okay, so we have gotten our FM output at the last plot. We need to do some changes here because it's really hard to understand what's going on here. Okay, so what we'll do, PLT dot figure, and going to change the figure size, right? So figure size, let's say 16 and 4. Okay, and yeah, let's run it. Okay, I see, like, right now it's kind of visible. You can see these higher frequency components right here, right here, right here. But it's still kind of hard to correlate, right? What's going on here. So I will just take like a small part, like from 0 to 0.2 seconds. Okay. So just going to do an axis here. So let's say PLT dot axis, and then we'll call 0, 0.2. Okay, and then -1 to 1. Okay, -1 to 1, and then run it. Okay, I think this worked on the first one, but we have to zoom in all the other plots as well, right? So copying this part and putting it right below here and right below here. Okay, so this should be good. Run it. Okay, so we have the message, we have the carrier, and um, we have the FM output. Now, still kind of hard to see what's going on here because the changes of frequency is so low. I can do one thing here, change the sampling frequency to 2000, okay, and see how that is going to impact. I think the plot is going to get a little smoother like this. And now you can see, like, the changes of frequency little bit visible once you have the plot in front of you. But I'm just going to increase this number m. So remember, I defined m before. This is the ratio of the frequency deviation and the message frequency, and also depends on the the modulator sensitivity, right? So let's make it 5. Okay, just to see the change. Okay, and now you can see this is the high frequency part right here, right? Because the cycles are coming up very fast, right? So this is depending on this part right here. So when we are going upwards right here, the frequency is going this direction, the message signal, the frequency is going higher. And when we're coming down, it is you see the cycles are kind of the the period is long, so that means the frequency, this is low. Okay, so this is high frequency, this is low frequency, high, low. So this is kind of doing the change in frequency. And it depends on this message signal, how that is going up and down. Okay, so I think I can do more changes. I can make it 7, just for experiment. And this is kind of getting obvious, like how the frequency is changing, with this with respect to the message signal. Okay, so let's go back to 1 again. And now we need to convert it into frequency domain. We want to see the spectrum. Okay, in the so we have to do the FFT. So let's say FM FFT is NP dot FFT, and then FFT. So inside the FFT, we have the FFT function, and we have to have this FM output, right? That's going to be the input here. So this is a time domain signal, and we are going to convert it to the frequency domain. So we got to have this FFT, okay, from this NumPy library. Okay, so let's run this part. There is no error, but we also need to convert this axis. This is a time axis, so we need to convert it into frequency, right? So the easiest way, to me at least, to do that is calling a variable fig, and then np dot f50, calling the f50 again, and then f50 freq. Okay, this frequency. So we have to have two inputs here. One is the number of samples and one is the delta t. Okay, so delta t is the sampling interval and this is the number of samples. So if we provide these two inputs here, we are going to get the frequency. Okay, n is not defined. I don't know why. I think I defined n. Oh no, I haven't defined n. So let's define n here. So n is equals to, let's say, 1, 2000. Remember the number of samples is like in 1 second is 2000. So n is 2000 right here. So let's run everything and go back right here. Okay, so now this line is already ran. One thing is, let's look into the freq. Okay, look into the frequencies. Okay, so this is, we have to kind of sort it. Okay, so to do the sorting, we have to call the index here. So idx is np dot argsort, right somewhere right here. Okay, and the input is the freq. So basically this is going to sort out the frequencies, okay, from this variable. So let's run that, and so this is sorted here from low to high. Okay, so now let's do a plotting. So plt dot plot. Okay, so in x-axis, remember we have the frequency, right? So let's call the freq, and but we want to have it sorted, so idx, putting this idx right here. Okay, and then we also need to have the y-axis, which is the fm output, fm out, and needs to be sorted, right? So idx. Okay, one thing is missing here. You see, like, I haven't taken the absolute value. Once you do the FFT, it's going to have imaginary components as well, right? So taking the absolute value here. Okay, and then run that guy, this guy, and run it. And oh, I have called the wrong variable. It's going to be fm f50, right? So let's call fm f50. Okay, okay, so now we have two things here. In the negative frequency, you know, like when you do FFT, there is a image, so that's right there, and this is the positive one. Let's look into the frequency, but before that we just need to look into the single side. So from just going to plot from 0 to, let's say, this portion 0 to 300. Okay, so let's say plt dot axis, and then let's say 0 to 300. Okay, only this portion right here, and y-axis is going to be from 0 to 1, because we are going to normalize this. Okay, we haven't normalized this. We should have normalized this, so we're going to normalize this. Okay, so this is the x and y defined here, and we can normalize right here. So max of this guy right here. Okay, so the max value is going to be 1. Okay, so let's run all of these again. Okay, I think this is the rounded bracket will be first here, plt dot axis, and then the round bracket. Okay, so let's run it. Okay, so we have gotten our plot. Okay, so you see our sampling frequency, our fc carrier was 200. So we get a peak in the carrier at 200, and these are the side bands, okay, on the left and right. On the left side of the carrier, we call it lower sideband, and the right side is the upper sideband. And how the sidebands are getting calculated here, remember we had FM is 20, right? So the first one right here, it's the carrier frequency, and the first sideband on the left and right, upper and lower, is calculated as FC minus FM and FC plus FM. Okay, so at 220 and at 180. Okay, and this is going to go on because this is defined in the Bessel function. If you go to the document, you'll see like there will be infinite number of the sidebands. Okay, and we can use filters and other processings, you know, to get our required frequencies. Okay, so these two bands here, right here, let me write that down again. So FC minus FM minus FM. This is going to be the lower sideband, the upper one, FC plus FM plus FM. Okay, so this is going to be 160 right here and 240. Okay, so this is how, if you go into this one, you have to have one more FM in both of these sidebands. Okay, so that's why I say like it's going to be infinite number of sidebands. Okay, so I hope you guys have learned something from this lesson. Have a good day.